Good afternoon, students. How are you doing this afternoon?
Good afternoon, sir. Doing good.
Doing okay.
Tan, you
Yes, sir.
missed something on Saturday. Me say you have some students who just show off. So come a class Saturday now and learn up with something them, you know. So proud of them. But never mind, we'll get an opportunity to go through it in our regular session. All right, I don't know where Mrs. Henningham. Let me see if I can give her a call to see if she's all right. If not, I may just start off. Give me a minute, please. Oh, so Miss is here. All right. All right, guys. Okay. So that last message, Miss. Stands. Appreciate it. All right, guys. So remember, we are running full speed ahead. So Mrs. When I start now so that I can then take over. So let me see. There are not many of us, you know, because I'm logged on twice plus Mrs. and that's three of us. There are only six of you here. Kimberly's long time I don't see in class, you know. You all right?
Yes, sir.
Okay. All right. Okay, Mrs. Senaham, you can go ahead.
Okay, thank you, sir. Good afternoon, everyone. I'm not sure if you're feeling as how I'm feeling, but you know, I'm putting God first. Thank you, God, for another day. And we're here to learn, to make the best of the opportunity which you have given us. And I'm appreciating life itself. In Jesus' name, amen. Any amen out there?
Amen.
Amen. We're putting the best
Amen.
foot forward. Nice. All right. So full speed ahead. We are still on limits and continuity, just supporting Sir, getting as much practice in. And I see where a few persons have responded to the matrices form I've submitted. Majority of the class have not. I'm encouraging you to go ahead, providing you with additional practice. Okay, the more you practice, the more you know that you'll get the correct answers in exam. Okay. Before I even share my screen, I saw this video. Let me ask, Sir. I saw this video from Khan
Academy?
Academy. Yes, sir. Is it okay within the framework of the school to share this 3 minutes video with the students?
Absolutely.
Okay. Thank you, sir. So, students, I'll be sharing this short video with you, and I'm sharing it because I think it gives a different, another perspective that which we have been trying to bring across. It's just for you to visualize and for you to see exactly what we're doing with limits and continuity. Okay, so let me share my screen. I'm one of those persons who work with several tabs at the same time. And yes, I'm still at work, but we are going to work together. All right, I need to share audio as well. Let me see.
Yes,
Tell
you
me.
do. Are you playing it now?
No, it has not started.
Functions
Let's see.
defined
Are you
like
hearing
h
it?
of y is equal to
Yes.
y
Yes, please.
squared, or f
Okay,
of
let's
x.
start over. Let's start over. Come on, go back on.
By now, we're used to seeing functions defined like h of y is equal to y squared, or f of x
This is
is
really
equal to
slow.
the square root of x. What we're now going to explore is functions that are defined piece by piece over different intervals. And functions like this are, you'll sometimes view them as a piecewise, or these types of function definitions, they might be called a piecewise function definition. And so let's take a look at this graph right over here. This graph, you can see that the function is constant over this interval for x, and then it jumps up to in this interval for x, and then it jumps back down for this interval for x. So let's think about how we would write this using our function notation. So if we say that this right over here is the x-axis, and if this is the y is equal to f of x.
So students, before I continue, the main idea here is that it's a graph, right? But it jumps from different locations along the y-axis. Are you seeing that? Students?
Yes, miss.
Yes, miss.
Right. So in your research, you just have to have an open mind as to what is meant, what do they mean by this piecewise function? Here is this function going at different levels, using different steps across the Cartesian plane.
Axis. Then let's see, our function f of x is going to be equal to, let's see, there's 3 different intervals. So let me give myself some space for the 3 different intervals. Now this first interval is from not including -9. I have this open circle here, not a closed in circle. So not including -9, but x being greater than -9 and all the way up to and including -5. So I could write that as -9 is less than x, less than or equal to -5. That's this interval. And what is the value of the function over this interval? Well, we see the value of the function is -9. It's a constant -9 over that interval. It's a little confusing because the value of the function is actually also the value of the lower bound on this interval right over here. And it's very important to look at that. This says -9 is less than x, not less than or equal. If it was less than or equal, then the function would have been defined at x equals -9, but it's not. We have an open circle right over there. But now let's look at the next interval. The next interval is from x is greater or -5 is less than x, which is less than or equal to -1. And over that interval, the function is equal to, the function is a constant 6. It jumps up here. Sometimes people call this a step function. It steps up. It looks like stairs to some degree. Now it's very important here that at x equals -5, for it to be defined only one place. Here it's defined by this part. It's only defined over here. And so that's why it's important that this isn't a -5 is less than or equal to, because then if you put -5 into the function, this thing would be filled in, and then the function would be defined to both places, and that's not cool for a function. It wouldn't be a function anymore. So it's very important that that when you input -5 in here, you know which of these intervals you are in. You can't be in two of these intervals. If you are in two of these intervals, the interval should give you the same value so that the function maps from one input to the same output. Now let's keep going. We have this last interval where we're going from -1. We're going from -1 to 9, from -1 to +9, and x, it starts off with -1 less than x, because we have an open circle right over here, and that's good because x equals -1 is defined up here, all the way to x is less than or equal to 9. And over that interval, what is the value of our function? Well, you see the value of our function is a constant -7, a constant -7. And we're done. We have just constructed a piece-by-piece definition of this function. And actually, when you see this type of function notation, it becomes a lot clearer why function notation is useful even. And hopefully, well, anyway, hopefully you enjoyed that. I always find these piecewise functions a lot of fun.
There we go, students. Any insight from the video? Is it the first time you're seeing the demonstration, or would this idea have popped up that this is how the function is represented on the graph?
First time seeing it, miss.
First time. Yeah. Miss Javia, you missed it, Javia. I have to send you the link. Right. So the graph is defined piece by piece, right? And with that understanding, it really intrigues me as to how this definition came about, because I was wondering, why is it? And then, yes, made the connection. Yes, we're having the different limits, and you can see the graph continuing, the function continuing, right? So where one ends, that's where the other continues. So even in our examples that we have been working in class, we can visualize it. Do your research. Now is the time for you to be posing questions to sir. Sir, I've been doing this past paper question, and I'm not sure how to. Come to class with your questions, okay? So thanks for listening in. I will share the link later for the video, all right? So what we're going to be doing now, we're going to be working 2 examples. Now that you have a visual representation as to how we are doing the piecewise function, right? Now we're linking it to continuity and discontinuity of the function, right? So just to get the class prep and ready for sir, we'll be doing this example. I know Taniel is ready. Right, Taniel?
Sure, miss.
Nice. So we're doing 2 examples today just to get us warmed up and ready for sir. What I can do is to play the video again when at the end, just a little snip the beginning. But at this point in time, I'm asking you to let us do this question. Enlarge this. We say f of x is continuous at x equal a if limit f of x when x extends to a is equal to f of a. At what point, or should I, or points, is the following function not continuous? What other word, what single phrase can you use for not continuous? Discontinuous. All right, nice. I'm giving you 3 minutes because we're giving sir maximum time today. Okay, 3 minutes. Let's start the discussion. So were we given an X value to work with? Given this question, at what point is the following function not continuous? How would you prove to say that the function is discontinuous at any or at the points for this function or over this interval, these set of intervals for the function? What is your idea in solving this question? Wait, I'm muted. Hold on, let me check. Are you hearing me?
Yes, miss.
Yes,
Miss, we
miss.
need to,
Yeah.
if the number is to the left of x, wait a minute, stop for me.
Can someone else, Tanil, in the meantime? How would you solve this question? Where are the x values are we focusing for this function?
It's the x minus 3, the x squared plus 1, and the x cubed plus 4.
Okay, these are the x values. Okay, what about using the intervals as an indicator as to the values that we can use? So this would be the intervals for the x values that we're substituting into the function. So these would be the linear, right?
Yes, miss.
Yes, miss.
Right. So how would you get the first x value? What is the first x value you would work with?
X is less than or equal to -1.
-1. Okay. So everyone is seeing that?
Yes, miss.
And what do you do next? Thank you, John Mark. What do you do next?
Miss, you're going to say the limit as x tends to -1 superscript minus because it's to the left.
So to the left and to the right of -1.
Yes.
And what are you checking for here? What are you checking for here?
Discontinuity.
Discontinuity, right. So let's see if my writing is any better this week. Okay. So if someone wants to guide me along?
Miss, you can write the lim as x tends to -1 superscript minus sign.
So what is this function here? We're putting it into, we're
X
substituting it
minus
into.
3.
Okay, nice. And what does this give?
-1 minus 3, which is -4.
Okay, nice. Okay. And what is the second?
The limit as x tends to -1 superscript positive sign.
So this is x tends to the right.
Yes,
Right.
miss.
And
Which
which
x
function is
squared,
that?
x squared plus 1.
What was the result you got, Tantan?
Mr. says since the limit as x tends to -1 superscript minus, which is x minus 3, is not equal to the limit as x tends to 1 superscript positive, which is x squared plus 1, f of x is discontinuous
Is this continuous?
at x equals -1.
Nice. Anyone get something different? Is there another response? Or you have not tried it as yet?
You said about the same thing.
You got it. Why is it that my number keeps on disappearing? You think the X, you notice that? Okay. So the same things All right, gone to the annotation now. Right, so what is the end result here?
Positive
So it's
2.
positive 2. Right, so we have that notation. So what is the other set of functions that we can test? What other x values we can test to see if it is continuous or not
The
continuous?
limit as x tends to 2 superscript a minus sign.
Nice. Can someone else, except from Tanil, share with me their response? What they have gotten for f of x for the limit of x tending to 2?
Miss, for the limit as x tends to the left of 2, I use x squared plus 1. And I got
Yes.
5.
And you got 5.
Yes,
Okay,
miss.
nice.
And as the limit
Nice.
tends to the right of 2, I use x cubed plus 4, and I got 12.
And you got 12.
So the limit as x approaches the left of 2 is not equal to the limit as x approaches the right of 2, then f of x is discontinuous at 2.
Okay. Is there any difference in response? Thank you, Shanti. Has anyone, they got something different? John Mark? You got
the same thing.
You got the same thing. All right, you see, sir. Have super. Your students are brilliant. They have gotten the responses. Nice, right? So here we have it. And ensure to write your notation. Okay, let's try another question. Good job, guys. Let's try another question. What is the value of the constant a in the following piecewise function to make the function continuous? Miss Green, Cassandra Green, long time I haven't heard from you. All is well?
Yes, miss.
Okay. Well, can you volunteer for this question?
Yes, kind of.
Okay, or to just tell us the idea in solving this one. How would you find the constant a?
Mister, can you give me a 60?
Sure.
Miss, well, starting with x equal 2,
Mhm.
less than 2, yeah, that. You substitute it with the 2 with the x, then you get a plus. Miss, you know, sure, miss.
I'm listening. Why you keep saying you're not sure? If you don't try it, we won't know if if what you're saying is correct, yes or no. And based on what you have been saying, you're on the right track.
Yes, if you substitute it, and it might add the 2, that will equal, like, it might add the 2 plus the 3, and then we get the 5. But that say a equal 5, but I don't think that's it, don't we?
Okay. Let it no ever well, I won't say simple, it's reasoning. So that's why I want to get your idea as to how to go about to solving this. So one hint I will give you, always refer back to your question. Remember, use what is available in your question. What does the question say? What hint is there? Very crucial point is there in the question.
To make the function continuous.
To make the function continuous. All right, Javia, are you able to pitch in at this time?
No, miss.
Okay. Let's go down the line. Matthew, long time I haven't heard from Matthew. How are you?
Fine, miss.
You're fine? Long
Yes.
time I missed you for what, 3 classes?
Yes, miss.
And you're fine?
I mean, I understand that with up on the screen.
Okay. Okay, that means you should be watching your videos of the previous classes.
Yes, miss.
Have you accessed them?
Not yet, miss.
You need to. You need to, Matthew. What I'll do, what I sent outside of that was in the WhatsApp group. Also, I'd sent a form. I'd sent a form of a matrices for additional practice. I'll send that to you as well. I believe you were here when we were doing the other topic form, right? I believe you were here. However, I'm asking, since Matthew is not that familiar, he has a lot of work to do. So we're going to rally around to see how best to assist him. So that means he would have missed all of piecewise function, all of the limits, right? Miss Kimoli, any idea as to how to solve this question? And using the hint that Tanila has given us?
So, miss, a function is continuous when it is defined. And when both sides are equal, so the left-hand side is equal to the right-hand side.
All right, stop
So-
there. Stop. Good girl. Miss Good. About good girl. Very good, Kimoli. So based on what you're seeing here, what is presented here, tell me the functions that would relate, the function that indicates the left-hand side and the function that would indicate the right-hand side.
Okay, so for the
Of-
left-hand side, that would be the first one where x approaches 2 from the left. So f of x is defined as ax plus 3. And the right-hand side is the second function where x approaches 2 from the right. And that's defined as 3x plus a.
So what are you going to, what did you say when you're defining ff? You're saying that the function must be, what was the second point you were making?
Where you said that the left-hand side must be equal to the right-hand side?
Yeah, so what are you going to do here?
So we're going to substitute in, well, we won't equate the equations.
Okay. You hear that, Matthew? Matthew, are you following?
Yes, miss.
So if you're going to equate the equation, as Kimoli said, would you be able to solve for A?
Yes, miss.
Okay, I'm counting on you to tell me the answer for A. Thank you, Kimoli. Do you care to help Matthew some more?
Okay,
So then I have the left hand side is ax plus 3 is equal to the right hand side, which is 3x plus a. We can bring both a's over one side. So transpose. Or you could substitute in the value for x first.
So you're saying ax plus 3 is equal to 3x plus a. That's what you're saying?
Yes, miss.
Okay. Matthew, big help you're getting, you know, and she's continuing. So you're saying to bring the x to one side. So
Well,
tell
the
me, what are
a's.
you doing? Or bring the a's to one side. Okay. So it's ax, right?
Yes. Minus a.
Ax minus a
Equals 3x minus 3.
I'm following what you are saying, you know. Come. Anything else?
So x, since x approaches limit, you can substitute 2 for x.
Okay. So this would be a2. I needed to write the function. Oh, guys, please ensure you write the limit first. So lim, you write that part of the question, x tends to, but since as I'm using this annotation, is not that easy to write here. Okay, ensure to write it and then we can continue. Okay, so a2 minus a is equal to 3x. Oh, you're saying 2. Is that it, Kimoli?
Yes, miss.
Oh, it looked like you're solving the thing for math yourself. All right, let's go. Continue. Good girl. So this would work out to be 2a. Or can we see what the left-hand side will work out to be? A is equal to what?
3.
Because you have 2a minus a, right? We'll leave it with a. So this right-hand side will work out to be?
3.
3.
Okay, Matthew, let's do the test. Thank you, Kimoli, and thank you, Tennille. Let's do the test, Matthew. How would we test to see if this the A is correct, A value is correct?
Let's say I go plug in the A in the function.
All right. And then you said that you don't know what is happening here, right?
I guess, Mr. Lemon.
Well, guess what? It's called what would it? We have dealt with intuitive approach, and you're using the same thing right here, and it's working. So that is how you prove it. So we're saying, let's go. 3. What is the value of x? 2. What is that equals to?
9.
9. Right? So what's the second part now? 3x. Very easy. Very, very, very easy. What is A? 3. And both of them
9.
equals 9. And what is the statement, Tanil? What's the statement?
Since the limit as x tends to 2 to minus ax plus 3 is equal to the limit as x tends to 2 plus 3x plus a. F of x is continuous at x equals 2.
All right. Thank you very much. Thank you, Matthew. Thank you for the other team members who have participated. Just dragging your memory as to the piecewise function. I think for Matthew's sake, I'm going to play the video again. Okay, Matthew? Let me stop sharing and I'm going to play the video again, a short video, then Sir is coming in afterwards. Thank you, guys. Stop. Let's go again.
By now, we're used to seeing functions defined like h of y is equal to y squared, or f of x is equal to the square root of x. But what we're now going to explore is functions that are defined piece by piece over different intervals. And functions like this are, you'll sometimes view them as a piecewise, or these types of function definitions, they might be called a piecewise function definition. And so let's take a look at this graph right over here. This graph, you can see that the function is constant over this interval for x, and then it jumps up to in this interval for x, and then it jumps back down for this interval for x. So let's think about how we would write this using our function notation.
So pausing here to ask the question. Let's see if I can get these off without losing. You're seeing the three graphs, right? The three function, the three representations on the graph, right?
Yes, miss.
Yes, miss.
All right. For those who weren't here when I first played this video, what do you think is the interval for this function here? Because these are functions that are represented here, right? And it is on a range, it is on the interval for the x values. What would be this interval here? This one. Minus. So x would be between
-5 to -1.
Okay. Right? And let's try this one over here. We're not talking about if it is less than or equal to or greater than or equal to. We're just using where it is from. And then we're going to introduce where if it is less than or equal to or greater than, or using the inequality sign. Okay. What about this one here? So this is looks like -1, -1 to +9, right?
Yes, miss. Yes, miss.
Right. So let's list note again.
So if we say that this right over here is the x-axis, and if this is the y is equal to f of x axis, then let's see, our function f of x is going to be equal to, let's see, there's three different intervals. So let me give myself some space for the three different intervals. Now this first interval is from not including -9. I have this open circle here, not a closed in circle. So not including -9, but x being greater than -9 and all the way up to and including -5. So I could write that as -9 is less than x, less than or equal to -5. That's this interval. And what is the value of the function over this interval? Well, we see the value of the function is -9. It's a constant -9 over that interval. It's a little confusing because the value of the function is actually also the value of the lower bound on this interval right over here. And it's very important to look at that this says -9 is less than x, not less than or equal. If it was less than or equal, then the function would have been defined at x equals -9, but it's not. We have an open circle right over there. But now let's look at the next interval. The next interval is from x is greater or -5 is less than x, which is less than or equal to -1. And over that interval, the function is equal to, the function is a constant 6. It jumps up here. Sometimes people call this a step function. It steps up. It looks like stairs to some degree. Now, it's very important here that at x equals -5, for it to be defined only one place. Here, it's defined by this part. It's only defined over here. And so that's why it's important that this isn't a -5 is less than or equal to, because then if you put -5 into the function, this thing would be filled in, and then the function would be defined to both places, and that's not cool for a function. It wouldn't be a function anymore. So it's very important that that when you input -5 in here, you know which of these intervals you are in. You can't be in two of these intervals. If you are in two of these intervals, the interval should give you the same value so that the function maps from one input to the same output. Now let's keep going. We have this last interval where we're going from -1. We're going from -1 to 9, from -1 to +9, and x. It starts off with -1 less than x because we have an open circle right over here. And that's good because x equals -1 is defined up here, all the way to x is less than or equal to 9. And over that interval, what is the value of our function? Well, you see the value of our function is a constant -7, a constant -7. And we're done. We have just constructed a piece-by-piece definition of this function. And
Okay, piece-by-piece definition of the function. So that's my takeaway, piece-by-piece definition of the function. So stop sharing. Sorry, is here. Any takeaway from you from the video?
This will open circle and shaded circle mean.
Yes, I took that away too. That's nice, right? When one is less than or greater than or and equal to, one is less than. Okay, nice. Anyone else? So what about the main point, the piece-by-piece definition of the function? So instead of having a continuous, have a piece-by-piece. It's represented here, and then it jumps, it takes a step up or down in the middle, but it's still the function. That is my takeaway. All right, over to you, sir. And thank you, class. Mr. Shan?
I'm here. I'm this unmute button wouldn't unmute at all. Goodness.
Yeah.
Thank you.
You're welcome, Kimberly.
Matthew, you have been absent, and you have not said anything to anybody, Matthew.
Yeah, a long story that.
Okay. All right. So thank you again for those who turned up on Saturday. I really appreciated the company, and moreover, quite a bit of learning took place. Quite a bit of learning took place. You were able to get, added information, a jump start that you will see in your class time again. So those who came should be ahead of the class. But you recognize, as I told you, that the syllabus is slightly different. Differentiation is differentiation. The syllabus is slightly different. So you are going into the differentiation more in depth compared to the business calculus students, because you are going to be looking at the trigonometric ratios. They are not doing any trigonometric ratios, right? I looked at the syllabus just now, and it says, for you, there's no piecewise. I mean, not piecewise, sorry. For you, there is no, I'm trying to share. For you, there's no first principles, but nonetheless, those guys went on and catch it. I don't want to start calling names because I can get myself into trouble. But I mean, every one of you who came out on Saturday turned up, and I'm wondering if I should put my business calculus class at this hour and put you on a Saturday morning. Trust me, the Saturday morning workout for Uno do good. All right, so let me just share with you what it is that we're going to be looking at. It says that I'm sharing, but okay, I know why. All right, so I've gone through all of this, the limits, indeterminate form, definition of continuity, and piecewise function, right? So I've gone through all of Unit 1. Unit 2 says differentiation, relate the derivative of a function with the gradient of a point of that function, which is what we started off with last week. Use the notation of the first principles. On Saturday, those guys saw it y dash, f dash, and dy by dx. Y dash, f dash, and dy by dx. So these are three notations that you need to know. It did say here differentiate polynomials. It says that a differentiation of first principles is not required. However, we are going to go into what it is that we did on Saturday also. And don't be no way, I'm going to do it with you today again. The rule for differentiation, when you're differentiating a constant, when you're differentiating a sum or difference. Then we're going to look at some differentiation involving sine and cosine functions. Notedly here that there is no tangent function that is here, but I will make reference to tangent. All right. It says apply the chain rule in the differentiation of a composite function. The students on Saturday were introduced to the chain rule. Differentiate exponential and logarithmic functions. That easy 1, 2, 3. That differentiate products and quotients, which was the next thing that we're going to be moving to on Saturday. So if you look, truth be told, on Saturday we would have gone through did all the trigonometric ratios, went through this, went through this, went through this. This is like the chain rule, not like the chain rule. This is the chain rule. We went through this. We went through the product rule. We never did a quotient. The first times the derivative of the second plus the second times the first. So we needed to go to, so we'd have gotten to about here on Saturday. And then we're ending off with stationary points, investigate the stationary points, and then we're moving into applications of differentiation. After the applications of differentiation, we move into integration, and that ends our differentiation, or calculus rather. So just to show you what has happened or is happening, you all have access to your syllabus on Educasoft. Matter of fact, I am not even the happiest camper as it relates to Educasoft, because again, you guys stop doing work and I will start come to class and make a horrible noise again. So remember, students, time is of the essence, and I'm giving you all the available options so that we can finish curriculum. You have to work with the process. All right. So with that said, you have access to your syllabus online, so please make reference to it. We looked at that. So let me just go through the second graph and just explain quickly. I send this off to you as a matter of fact, I don't think I should go through it because I send it off to you. How many of you were able to look at the graph? Did you do anything with the graph that I sent off? And no, I sent it off. Could be early Saturday morning, it's not Friday night, Saturday morning. All right, let's go. So it says, given a function f of x, which is going to be equals to 2 minus x squared, we need to find the gradient at the point 1, 1. So the coefficient of x squared is negative. The coefficient of x squared is negative. It has a negative x squared there. The coefficient of x squared is negative. When the coefficient of x squared is negative, the graph shapes like an N. Look, watch me, very important, especially when I'm moving to stationary points. Extremely important, especially when I'm moving to stationary points, when you're going to be required to classify the nature of the critical points. You're going to be asked to classify the nature of the critical points, so you need to know what happens. the parabola is a U. Normally we say when the graph shapes like a U, the graph is positive. It is shaping upwards. It's a positive graph. A smile, some teachers teach it as a smile. When it's a frown, some teachers say it's a negative graph. I don't use that. I say N for negative. You see, it looks like an N, a very wide N. But N for negative. How do you know it's a negative graph, sir? Look at the coefficient of x squared. The coefficient of x squared is a negative sign. The coefficient of x squared here is positive. Once the coefficient of x squared is positive, you are going to have a U-shaped graph every single time. Once the coefficient of x squared is positive, you will always have a U-shaped graph. Once the coefficient of x squared is negative, you will always have an N-shaped graph. Notice I said x squared. I don't want anybody to go and misrepresent me with negative x cubed. That's a different shape. I'm speaking about my squared graph. These rules only apply to my quadratic graphs, meaning I have an x squared term. If x squared is positive, the graph shapes like a U. If x squared is negative, the graph shapes like an N. Do you have that? Or I need to repeat myself.
Get it, sir.
All right, good. Now, similarly, it says to find the gradient at the point 1, 1. 1, 1, if you see I'm a Cartesian plane here, 1 for my x-axis is corresponding to 1 on my y-axis. So this point here, where you see the crosshairs, is corresponding to 1, 1. When my x value is 1, my y value is 1. That's what it corresponds to. Now I need to find a gradient at that point. I need to find a gradient at that point. Now in finding a gradient at that point, I'm going to draw graphically. See, it says the graphical method. Graphically, I'm going to be drawing a tangent at that point. So what do you mean by at that point? By definition, a tangent to a curve is that line that touches the curve exactly at one point on the curve. Angle 1. Angle 1 point. Not 2, 1 point. So I'm drawing a tangent to my curve that touches it exactly at 1, 1. Now what I'm going to be doing is completing my triangle. So you see my orange line and my red line, my green line shapes what my triangle is going to be. It's y2 minus y1 over x2 minus x1. Similar to what it is that I did last class, rise over run. Really don't have the time to do all of that detailed drawing. You have the information already. As a matter of fact, I sent you off these notes. So it's going to be y2 minus y1. Y2 is going to be 1 minus y1. It's going to be negative 1. So it's going to be 1 minus 1. Something's not correct with my calculation here. It's going to be 2, 1. Right, so it's going to be y2 minus y1, so it's going to be 1 minus 1 over 2 minus 1. Something is not right. Let me verify it. I'm looking at it and I'm not seeing something is off.
Get the next point.
Huh?
But you get the next point on the line. Because I only understand the 2 negative 1, but I'm not sure you get the next point.
Which point? This point?
When I calculate the gradient for the tangent to the line.
Yeah. Give me a minute. Something is off right there. I'm just checking it, Matthew. 0, 1, 2, 3. No, so this is going to be 2. This is a point. This point here corresponds to 2, 1. Right? This point here corresponds to 2, negative 1. And this point here corresponds to 1, 1. Y2, my right, Y2 is 1. Now Y1 is negative 1. Oh, that's what I did. I'm supposed to be having 1 minus 1. I have negative 1. Can you see that? I'm supposed to be having 1.
Yes, sir, it's supposed to have a positive 1.
Supposed to be a positive 1, right? That took me a while to find out, to figure out. Wow. I know what this is. I'll bet you any money, say. Oh, come on, my system is slowing up on me again. Come on, system, come on.
Sir, so you're looking at wherever the points intersect with
Right.
the... Okay.
All right. Okay, so it's supposed to be Y2, which is 1, minus 1, Y2 minus 1 good, over X, which is 2 minus 1, which is 2. So this is 2 over 1. No, man, something's still wrong. Oh, something's still wrong. The graph is negative, so that means I suppose I have a negative value. This is 2, negative 1, 2, positive 1, 1, 1. Y2 is 1 minus a negative 1, so that becomes positive 2 over 2 Oh, come on. All right, I'm not seeing this one. All right. My eyes kind of foggy. Let me move on from there. I'm coming back to this. I'm coming back to this one. I still answer you, Matthew. Something is not right there, so, and I am not seeing it. I'll get back to it. I'll soon fix it. All right, so let us move to here, because all of this, you notice I said later on we'll see the approach. Let us just jump to that approach, which is here. So we're going to be looking at the notation for the derivative. Y is equals to f of x. Y is equals to f of x. I'm going to have y is going to be equals to x to the n. So y is equals to the function in x. Y is equals to a function in x. See the function here? What is the function? X raised to the n power. So you can have one function also. It's a generalized function. It's a generalized function. So y is equals to x to the n. Now watch me. When I'm differentiating, I'm taking this power and put it as a coefficient of x, and then I'm reducing the power by 1. Watch me. X raised to the nth power, I'm taking the n, I'm putting it as a coefficient of x, and then I'm raising it. I'm subtracting, I'm reducing the power by 1. So watch me. Y is equal to x to the n. dy by dx is going to be n x raised to the n minus 1. Note, the power becomes a coefficient and the power is reduced by 1. The power becomes a coefficient and the power is reduced by 1. The power becomes a coefficient and the power is reduced by 1. Y is equal to x to the, and I'm deliberately taking it slow. So don't fall asleep. I'm deliberately taking it slow. Y is equal to x raised to the nth power. Dy by dx is going to be equal to n x to the n minus 1. See here, sir? Dy by dx is equal to n x to the n minus 1. Then, sir, what is dy by dx? Thank you for asking. It is the rate of change of y with respect to x. Let me not use my negative graph and go back to up here. This one is perfectly fine. You notice I have my rise over run. It is a change in my rise. So we get change in rise. Teacher, y2 minus y1, you're looking at the change in y over the change in x. So it's the rate of change of how y is operating by the rate of change of x. So I'm looking at the change in y over the change in x. And that gives me, that ratio gives me my slope, my gradient. So dy by dx is really talking about a change in y over a change in x. And see here, it depicts it nicely. Y2 minus y1 over x2 minus x1. Y2 minus y1 is the change in your y value. See here, dy is a change in your y value over x2 minus x1, a change in your x value, which is our run. Dx. So whenever you see dy by dx, it is the rate of change of y with respect to x. It is a rate of change of y with respect to x. It is a rate of change of y with respect to x. It is how y changes compared to x. One works in tandem with the other. One cannot work without the other. They are both married. Matter of fact, I was looking at the outline just now. Let me just switch and show you. I was looking at the outline just now and see where those, I don't want to call them wicked. Um, 4.8, which is differential equations. Look at that 2 minutes, please. So when I get to differential equations, you will see me, and it did say variable separable. That's what it said? Yes, it did say variable separable. So that's the method we're supposed to be using, variable separable. So when I get to differential equations, you will see me separating my dy by my dx. All right? Funny enough, I was home yesterday, Sunday, preparing notes on differential equations for my calculus students, calculus 1, calculus 2 students. So I only just recognized that it is here. So those notes will come in handy for you guys. I have a couple of them, about 4 or 5 of them just to go and type now. All right? So my dy by dx, we will move with the variable separately here. but my dy by dx is my rate of change of y with respect to x. All right? Now, note f of x is equal to y, but sir, a while ago you said y equals f of x. It's an equal sign. It can be read from the right to the left and the left to the right. My first derivative is going to be f dash of x, or I can have it as dy by dx, or let me just show you what I'm doing here. The syllabus says to show you y prime, f prime, and dy by dx. So use a notation. So I've done this piece already, you know, with the graph. I'm using the notation now for the first derivative of the function. So let me just do an amend here. Easy. All right. So my first derivative, I can use either f dash of x, I can use dy by dx, I can use y dash of x. So any one of these notations you see, it works. It works. Any one of those notations work. The other ones, could be f double dash. If f single dash is the first derivative, f double dash is the second derivative. If dy by dx is the first derivative, d squared y by dx squared will be the second derivative. If y prime or y dash of x is the first derivative, y double prime is going to be the second derivative, and so forth and so on. F triple dash will be the third derivative, or I can use d cubed y by dx cube or y triple dash of x. All right? So those are the notations that you are supposed to be comfortable with. And that's our 2.2. That's all I want us to do in 2.2. So what I did was also go into the syllabus and just write down what it is that they're asking. They're asking us to, asking us to show you the notations. So go again. 2.2 is finished right here. Y is equal to x to the n. I'm supposed to show you my dy by dx. My dy by dx can be either f dash of x, y dash of x, or I can use dy by dx. Any one of these three notations is permissible. So if you see me use dy by dx a whole heap of time, but to go into the exam and see them use y prime or f dash or y dash, best believe that they're speaking about the derivative. It's very important. All right? Any questions regarding this one?
No, sir.
All right, let us look at the differentiating polynomials. Come on, computer, don't be playing with me today. Sure. RECALL. Okay. All right. So recall, I'm going to recall this. All right, recall. Y is equal to x to the n. It implies, that sign means implies. Y equals x to the n implies that dy by dx is going to be n x to the n minus 1. I'm putting the n in front and I'm reducing the power by 1. Let's go. Y equals x cubed. Y equals x cubed. So what would have happened on Saturday? The students would have seen me go through, some of your classmates would have seen me go through first principles, which is just another extension of limits. And because they understood limits, it was so easy for them. I gave them difficult questions and they were able to do it. Very good again, guys. Now, y is equal to x cubed. And they're asking us to differentiate. Look at what is going to happen. This 3 is going to come in front of here, and I'm reducing the power by 1. So I'm going to have 3x to the 3 minus 1. See it right here, so? And 3 minus 1 is 2. So my dy by dx is going to be 3x squared. Tell me if you see that. And if you don't,
Yes, sir.
very nice. If you don't, let me know what it is that you're not seeing. Okay, give you enough time. So it did say we need to look at polynomials. The syllabus says we need to look at polynomials. Right? It says to differentiate polynomials. Those are constants. And we're looking at the chain rule in 2.3. So we're looking at the chain rule, sums and differences, constant, and x to the n is n x to the n minus 1. All right, so I'm looking at 4 things. Now, that's a polynomial. This is a polynomial, but specifically it's called a monomial. Mono means what?
One.
One term, very good. So it's a polynomial, but more specifically it's called a monomial. This is a polynomial, more specifically it's called a?
Repeat, sir.
This is a polynomial. This one is a polynomial, but more specifically it is called a?
Trinomial.
It's called a trinomial. And trinomial, the tri means 3, 1, 2, 3. But certain among quadratic expression that too. Absolutely. Absolutely. So I can tell you that I have a quadrilateral. Okay, which one? Because I have so many quadrilaterals. All right? So I have a whole lot of polynomials. So I can name them a monomial, a binomial, a trinomial. We can go to a quaternomial, you know. But guess what? We don't have time to call it quaternomial. So when we have a monomial, we just call it a monomial. And when we have a binomial, we just call it a binomial. When we have a trinomial, it's a trinomial. But once it is that it's greater than 3 terms, we're not going to say it's a quaternomial or a synconomial. No, sir. We're just going to call it polynomial. We don't have time to go through and use in Spanish. No, sir. We just call it polynomials. All right? Let us go. Watch me. I'm using this 2 to multiply the negative 3 right here, because this is negative 3, and I'm taking this 2 in front of it, so it's going to be 2 times negative 3 is an. All right. Let me do something first. Rearranging I'm rearranging here. I'm rearranging here. So that's a question. I'm rearranging. Why am I rearranging? You don't have to rearrange. I'm going to rearrange with emphasis here. I'm calling this negative 3x squares. I'm saying this is negative 2x to the first power. Do you agree that it's to the first power?
Yes, sir, because there's only one x.
Very good. And then now, watch this magic. This negative 3 is actually x raised to the 0 power. Because anything raised to the power 0 is? No, man. Is?
Sorry, 1.
Is 1. Very good. So anything raised to the 0 power is 1. Numero uno. Anything raised to the power 0 is 1. Numero uno. But we don't write a constant and put x to the 0 there. No, sir. We don't need to do that. We don't write a constant and put x to the 0. But I want you to know that this x to the 0 is important, is right here. And there is a specific reason that I want you to put it there. And I will tell you the story a little later on. It's a very nice story. And I'll tell you that story a little later on. Let's go to it now. So this 2 is going to multiply this negative 3 to give me negative 6. And of course, I'm going to reduce the power by 1. So it's going to be 2 minus 1, which is right here. This one is going to be used to multiply this negative 2 to give me negative 2. And then I'm going to reduce this by 1. So it's going to be 1 minus 1. This 0 is going to multiply this -3, and I'm just going to get -0. Anything raised to the power 0 is 1. But more importantly, the differential of a constant is equal to 0. See the -3 here? It is a constant. So why do you call it a constant? It stands alone. It don't have no baggage. You see that one here? The -3, married. X squared. Anywhere him go, the wife go with him. And in no shape or form am I calling the wife a baggage. Anywhere him go, the wife is there. Anywhere this one go, the wife is there. But this one here, not married yet. So the differential of a constant is always equals to 0 every single time, barring none of the times. The differential of a constant is equals to 0. So why? See it here, so? Because when I have a constant, it means that the variable behind the constant is going to be x raised to the power 0 if I'm in a function with x. If I'm in a function with t, it's going to be t raised to the 0 power. And when I multiply the power 0 by anything, I'm going to get 0. So the differential of a constant is equal to 0 every single time. So my final answer now is going to be -6. It's going to be -6x, because 2 minus 1 is 1. We never normally write the 1 up top. All right? It's understood to be so. And 1 minus 1 is 0, and anything raised to the power 0 is 1. So I'm just going to have -2. So my differential for this function is simply going to be -6x minus 2. Are there any questions?
No, sir.
All right. I know you wouldn't have any because you did very well. Let's go. Let's go. Let's go. I'm given a function 4x squared plus 3x minus 1. And I'm asked to differentiate. I'm asked to differentiate. It is important that I name my function. It is important that I name my function. Now, Mrs. Henningham may say, I want to name my function f of x. So she's going to say, let f of x be equal to this function. So she's naming her function before she starts differentiating. So she cannot just start differentiating without naming the function because she don't really know how to call the function. She don't know how to name the function. So she has to name the function first so she can represent what the differential is going to be. So let's go with this differential. So I know f of x is there. So therefore, when I'm differentiating, it's going to become f dash of x. See here? F dash of x. F dash of x is suggesting that I have the first derivative. F double dash of x suggests that I have the second derivative. F triple dash of x suggests that I have the third derivative, and so forth and so on. Now, this 2 is going to multiply this 4 to give me 8. I reduce this by 1 to give me the first power. The imaginary 1 that is up here will multiply this 3 to give me 3. And once this is 1, you know that when I differentiate, I can get 1 right here because anything raised to the power 0 is 1. But remember, the differential of a constant is equal to 0. Mr. Shan decided that I don't want to name my function no f of x. I will name it h of x. And I name my function h of x, which is 4x squared plus 3x minus 1. When I differentiate it, I'm going to get the same function. 2 times 4 is 8, reduces, becomes 1. 1 times 3 is 3, reduce it, I get x to the 0, which is just 3. And the differential of a constant is equal to 0. So I have 8x plus 3, 8x plus 3. Then, sir, how many marks Mrs. Cunningham will get? Compare the number of marks that you will get. We get the same number of marks. Then, sir, what if I never name the function, but I still get the 8x minus 8x plus 3? You won't get the full mark because the function must be named. If they don't give you the name of a function, you have to name the function. If they give you the name of a function, use the function name. You can't change it. You know, like some girls that walk on the road and say, "Hi, daughter, what's your name? Candy." And she turned the corner, "Hi, daughter, what's your name? Doreen." So by the time she reach up, she have 1,000 names. She walk on the road again and him say, "Candy." And you know, look back, "Candy." And you know, look back, I don't know Candy name. Right? So the function must be named so that when you're doing your derivative, you can associate the name of the function appropriately. And you know why it is important for you to do the name? Especially when you're looking at graphs. You know, most of you are aspiring scientists, forensic, medical doctor, engineer, you name it. You know what's important it is, especially if you're a civil engineer and you go there to take some soil sample because you want to know what how to put on the road surface. Because if it was a cane piece that you want to run a road through, you know, so the soil is soft. So you have to make sure that you compact the soil. So you're going to use gravel to compact, then marl, so at least it has a firm foundation. It's very important. Very important. The attention to detail. If you're a medical doctor, when you're taking samples, you can't just take different blood samples and just screen them down. You have to name them. Because if one of the samples is contaminated, you need to know one, let the right person know that it's contaminated. I laugh. Oh boy, Jamaicans are the best, you know, trust me. You know, when you look at social media, them say Jamaica isn't a real place. I've heard of a story, don't know how true it is, of a man wanting to get on the farm work program. Man dying to reach a foreign to get on the farm work because guess what? The man said that it was a ticket out of poverty. But guess what? The man smoke him something. And them don't tell it, say, if them find it in the system, you can't go on the man decide, say, this is an opportunity and no miss me. So he was supposed to take in a urine sample. So he said to him, girlfriend, you better give me your urine sample because guess what? If me give them my urine sample, they're going to see there's something in my blood. And guess what? For me, I'm going to make things better for me and you. And the man go in and give him urine sample and come out and think, say, yeah, everything crisp, coming on my wife, all right. And the man go back now for the other final interview and think, few them say, congratulations, sir, you're pregnant. Because he never knows his girlfriend pregnant. And them know that sample was not from a man. It was a woman because the sample come back to being that he's pregnant. So you don't know what happened to him. Him not get an opportunity at all to go on the program because right there say him lie. And them say if you lie, you're a thief. And some of the questions them put on the form say, do you have plans to come back or to run off? So the man them going to say, so the man them going to say, if you can do that, I ain't not reach yet. What happens when you reach? All right. So we have to have key attention to detail as science students. Very key attention to detail as science students. All right. All right. So let's go. So it doesn't matter how it is that I name it, as long as it is named. Very important. As long as it is named, very important. Let us look at this example 4. And these are all chain rules. If you notice what I'm doing here, I did say that we need to look at the sum and difference. If you have a sum and difference in it, again, I have no sum, but I just have difference. And here I have sum and difference. So technically, I am going through our 2.3. All right? Really not a difficult topic. If you follow the moves, you'll see what is happening. Watch me now. It says to differentiate g of x. G of x does not look pretty. G of x has a cutish look, if you know what I mean when I say cute. Look to it. 1 over x to the 7 plus 3 over x to the 5 minus 4x squared minus 6x. No. No. That's not supposed to be there. Just minus 6. What is wrong with me tonight? Minus 6. So look at what I'm going to do. I'm going to rearrange a function. Well, let me just do the recall first. I want you to recall two things for me. 1 over a to the positive n is going to be equal to 1 over a to the negative n. When I reciprocate, the sign changes. When I reciprocate, the sign changes. 1 over a to the negative n, when I reciprocate, it becomes 1 over a to the positive n. So think of it this way. If you have a negative power in the denominator, when you reciprocate it and get it to the numerator, it becomes positive. If you have a positive number in the denominator, when you reciprocate and put it into the numerator, it becomes negative. Very important. Very, very important. All right? But look at what we're doing. We did indices. That was the very first topic we started. We did indices. 1 over x to the 7 is the same thing as x to the negative 7. True or false?
True.
True.
All right. So you see what I'm doing now? This 1 over x to the 7, I'm renaming it as 1 over 1 x to the negative 7. All right? 3 over x to the 5th, I'm calling it 3x to the minus 5. Because this positive 5 is in the denominator. So in the numerator, it becomes negative. In the numerator, it now becomes negative. And then I'm going to wrap it up.
Sir.
Are you hearing me?
Yes, sir.
Yes, sir.
All right. Sorry about that. I'm actually using the audio for my cell phone, and the cell phone rang, so it just chip it out. Okay. So I'm differentiating now. So I'm going to say negative 7 multiplied by 1 is a negative 7. And I'm reducing my power by 1, but you have to be careful. When you have a negative power and you reduce it, it's not going to become negative 6. It's going to become negative 8. Because negative 7 minus 1 is a negative 8. And this negative 5 times 3 is a negative 15. And I'm reducing the power by 1. Negative 5 minus 1 is a negative 6. It's going to be negative 15x to the negative 6 power. Which is this term. And this 2 times this negative 4 is going to be negative 8. I reduce it by 1 to the first power. I don't have to write to the first power. And remember, the differential of a constant is equal to 0 every single time. Are there any questions? I've gone through 4 examples. Are there any questions?
No, sir.
No, sir.
All right. Question. The ones who are not talking to me. Oh boy, Lord, save us. The ones who are not talking to me. Are you seeing what it is that I'm doing?
Yes, sir.
Okay, very good. I'm happy, and I'm not gonna kill it. I want you to do that one for me, please. Number 4. I want you to do number 4 for me. Y is equal to 7x squared minus 3x minus 6. I want you to differentiate for me, please. Now that the function is named y, you're going to differentiate it dy by dx or y dash of x. And incidentally, differentiation is not a 3-page here, 1 line. Let me know when you're done, please. Y is equal to x to the n, dy by dx is going to be n x to the n minus 1. Y is equal to x to the n, dy by dx is going to be equal to n x to the n minus 1. You take the power and multiply it in front of the coefficient there of x, and we reduce the power by 1. And you reduce the power by 1.
Finish, sir.
Okay, thank you, Tantan. What did you get for your answer?
I got y prime x equals 14x minus 3.
Okay, very good. And I had it as dy by dx, but guess what? Same difference. Did everybody get that? Manisha, well, I know you get that,
Yes,
Manisha.
sir. Yes, sir.
Yeah, I know. I don't know why I caught up on you because you did it very well on Saturday. Kimoli, you were praising God on Saturday. Do you get that now?
Yes, sir.
Okay, cool. Johnny, we tell you, you're supposed to always talk to me in class, you know. Good afternoon, sir.
Afternoon, sir.
Yeah, you remember that from Saturday?
Yes, sir.
Nice. Shanti, I won't call upon you. Kamisha, you understand that? Kamisha, do you understand? Nikki, how you stay? Oh, okay, Kamisha, you answered yes. Nikki, how you stay?
Good, sir.
Yeah, mommy know you good, mommy. That's why I make sure I say there. That's why I call upon you. There's this Georgiana person that don't even talk to me in class. All right, let's go. Numero 5. Quick time. Somebody just tell me the answer, please. Quick time. Mental.
4x plus 5.
4x plus 5.
Duh, 4x plus 5. Very good. Foxy, you see how you get that? Well, you're supposed to see that, Foxy, or it's leaving a fall out.
Yes, sir.
Oh, okay. Very nice. Be so bright. Oh. I saw them teach you one, you know. Then give it a nice one in the class, and then after that, no, then give the one, then we half of the one myself. Not go so. I am sure none of you will get this one right. Can you try number 6 for me, please? You may need to write it. Try 6 for teacher for me, please. Anybody? Somebody?
Sir, negative 2x minus 4.
Minus 4.
Yes, sir.
I only heard negative 3x. Negative 3x what?
Minus 4.
Wow. Negative 3x raised to the negative 4. Very good. All right. Now, I have a bit of stuff here because, I mean, that's a chain rule, guys. The chain rule really talks about the sums and differences. The chain rule, think of a chain. Think of a chain. You have several linkages in that chain. And God forbid, if a chain grabber comes and grabs the chain from your neck, it's going to get busted at the point where it's very weak. But if the chain strong, he might go draw you with him because the chain now able to leave the neck. All right? So look at what happens here now. If I'm giving you x cubed and I ask you to find f dash of x, it's going to be 3x squared. Do you agree with this 3x squared for the first derivative?
Yes, sir.
Yes, sir.
Yeah, man, that's the first derivative. Look at what I can do. I need to change this to also. It can be called dy by dx, or I can call it as y prime of x. All right? That's who fix that. And my f double dash. Now, if I'm trying to find the second derivative, I will have to find the first derivative and differentiate the first derivative one more time in order to find the second derivative. I'll have to find the first derivative, differentiate the first derivative once more in order to get the second derivative. And the third derivative, I'll have to use the second derivative in order to get it. So let's go. So when I differentiate this first derivative one more time to get the second derivative, it's going to become 2 times 3, it's going to be 6x. And when I differentiate the second derivative, I'm going to get 6. What happens if I differentiate the third derivative? What do I get?
0.
6.
Okay, the correct answer came first. I'll get 0. Why do I get 0? Because
The differentiation of a constant is 0.
every single time. Yesterday, today, and always. And sir, show you why comes that the differentiation of a constant is equal to 0. Why, sir? Because a constant like negative 3 has behind it x to the 0. Let us again investigate our trinomial. Our trinomial here is x to the second power, then x to the first power, then this one has to be x to the 0 power. And if we're using this number to multiply these numbers in front, and this one to multiply this negative 2 to give me negative 2, it means that I have to multiply this 0 by this negative 3, and it's going to give me 0. suggesting that the differential of a constant is equal to 0 every single time. Yesterday, today, and always. So the fourth derivative here is going to be equal to 0. The fourth derivative is going to be equal to 0. The fourth derivative is going to be equal to 0. You see me here, I was trying to figure out in my headspace, how am I going to denote this stuff here? And then Father God, hey, God have a sense of humor, man, Jesus. You know, much time I sit in class and say, Lord, how am I going to make them understand something? And I'm saying, I don't have enough space, Jesus. How am I going to do it? Father God said, just put y dash is equal to dy by dx is equal to that, since you have the f of x so trace already. Yeah, man. So f of x, y dash, f dash of x, y dash of x, dy by dx, all of these are the same thing. Right? Same thing.
Sir, is there a case when they tell you which one's the right?
No. Not so. Well, let me quantify that. No. So if they name the function f of x, they are expecting you to use the f function. If they name the function y equals, they are expecting you to use either y prime or dy by dx. Sometimes the question gives you y and the question will say find dy by dx. So they're asking to find dy by dx, you won't go ahead and write y prime because they're asking to write it in dy by dx. And there are other times they don't name the function for you, and then you are going to be required to name the function. If you are required to name the function, use any notation you want, right? But in other instances, however they write the question, you're going to be guided by that for the notation. If they give you f, that means they want it in f dash of x. If they give you y, you can either write y dash of x or dy by dx. Sometimes they give you y and they say to you, comma, find dy by dx. It means they don't use y dash, use dy by dx. Get me?
Yes, sir.
All right. Now, I'm going to pause right here because the next thing on the syllabus at 2.4 asks me to look at the differentiation expression involving sine and cosine functions, which is not very long. Not very long. I mean, I wrote quite a bit of questions, but it's not very long. And I don't know why I wrote it like that when it is that. All right, so I can't do this one. I can't do 6 yet. I can't do 7, and I can't do 8. Because I wouldn't have done. I would have done product 2. I mean, I have the rules here, but it's just that I need to sequence the stuff. Sequencing is very important. Let me show you what they have. After 2.3, in terms of doing the chain rule, sums and differences, the constant and y to x to the n, what they have here now is differentiation expression involves sine and cosine function. All right. So I'm just going to give you the basic ones with sine and cosine, then apply the chain rule in differentiation of composite function. That's what we were doing just now. We're applying the chain rule in composite functions. I may write 1 or 2 more questions and give to you. That's exactly what we're doing. And then now to move into the exponential and the logarithmic function. But the application of the chain rule in differentiation of composite function would be things like these up here, right? All right. So let me go 1, 2, 3, 4, 5. I'm not going to go beyond 5. INVOL involves the PRODUCTROULE. All right. I don't do the product rule with it yet, so I can't. It would be unfair for me to go through that. When I do the product rule, oh, I know why I did it. Okay, got you. I know why I did it. So if you look at my notes, you'll see all of here alone deals with trigonometry. All of these here deals with trigonometry. Because I didn't separate this stuff, because those of you who were there on Saturday would recognize that I did some of these questions were some of the same ones that I use, because what I prepared for them on Saturday, I wrote these specifically for you. These 8 questions I wrote specifically for you because the Calculus 1 students are not doing any trigonometric functions. So I just, instead of preparing 2 different things, I just do, 2 birds with 1 stone. So no one understands why I did what I did. All right. So having gone through that, we're supposed to be differentiating some functions, expressions, involving sine and cosine functions. Now, the differential of sine is cosine. The differential of sine is cosine. Y is equal to sine x, dy by dx is going to be equal to cosine x. However, the differential of cosine is going to be equal to negative sine. The differential of cosine is going to be equal to negative sine. The differential of sine is equal to cos. The differential of cos is equal to minus sine. The differential of sine is equal to cos. The differential of cos is equal to minus sine. The differential of sine is equal to cos. When I differentiate sine, I get cos. But when I differentiate cos, I get minus sine. You have to remember that. The differential of sine is cosine. The differential of sine is equal to cosine. I am pausing deliberately so that you can run it through your head space. The differential of sine is equal to cosine. The differential of cosine is equal to minus sine. All right, watch me. Let us look at example 1. Y is equal to sine 2x. I'm going to differentiate the function. I'm differentiating the function. What is the function? So the function is sine 2x. Okay, let us speak sines. Let us speak sines. Let us speak sines. When you look at an element, tell me where's the nucleus of that element? Where do I find it on the element?
The center.
The center, very good. The center. When I have ionization of an element, and the element either accepts or gives up an electron, where it come from? Where does the electron come from?
The shell.
The shell, because I was about to say to you a while ago, I have Mrs. Thomas on speed dial. So I'll call her now or ask her to come into my class and see how well you guys are answering this. All right. So you remove it from the shell. The number of protons equal the number of
Electrons.
Number of electrons. So when you move an electron from the shell, are you removing any protons from the nucleus of the atom itself? Say no.
No.
Good. And this is how you have the ionization taking place. So what do you mean? And I'm speaking this because I know most of you are science students. All right? This is how the ionization takes place. So the nucleus will end up having a different number of protons compared to the number of electrons. Electrons are negatively charged, protons are positively charged. So when you add those two, this is how you end up getting a plus charge and a minus charge. And this is why chlorine is going to be Cl minus. Because one of the electrons, chlorine is accepting one of the electrons to its outer shell, so it is that it can obtain a stable octet. So the EC is going to become 2,8,8. Chlorine has one more electron compared to that of the nucleus. That is 17. Chlorine now has 18. So positive 17 minus 18 is equal to negative 1. So when chlorine ionizes, that's why it forms a Cl minus 1 charge. Don't you all knew that? Hello? Okay. All right. So that's where you end up getting the charges on for your stuff. All right. Why did I do that a while ago? Because I'm making a connection between math and chemistry. Incidentally, when I did logarithms with you, this is how it calculates the concentration, the pH concentration. Jesus, wait again. It is a negative log of the hydrogen ion concentration. That's where you go. You know, not studying chemistry, you know?
Sir,
Sir, I lost here. We did that, sir. When I remember that, sir.
Hello, here, you know, when I was doing A levels, I never did CAPE like you guys. When I was doing A levels, you know what we had to do? Study everything in lower 6 and upper 6. And at the end of upper 6, we get tested on everything from first year into second year. Unlucky is when you get in first year, only get tested on it, and then only get something new. You're not supposed to all get A's. We had to study everything and then test it on everything one time. But anyhow, the point I'm making is, if it's just like we can't get into the nucleus of an atom to interfere with it, you cannot get into the, watch me, you cannot get into the center of the angle and interfere with it. So you can't say sine is one thing and then the 2x is something else. No, this is sine 2x. This here goes with this every single time. Just as how I can go into the nucleus to interfere with anything, the nucleus is fixed. You see how far the nucleus there? Protected by all of these energy levels. You can't go inside there for go trouble. It's only the valence electrons alone that you can deal with. We can't go inside of the angle and go interfere with it. Watch this angle. So the angle is big, 2x plus 1. We can't go inside it, go trouble it. I shall not trouble it. It are illegal. So just as how you can remember the chemistry, well, hopefully, I really want you to remember this in the math. You cannot go inside of it to interfere with it. It is illegal. So watch me. So if we know that the differential of sine is cosine, therefore the differential of sine 2x must be cosine 2x. See it here, so? Cosine 2x. If the differential of sine is equal to cosine, it simply means that the differential of sine 2x is going to be equal to cosine 2x. But I must now differentiate the angle. And the differential of 2x is going to be 2. So now I have 2 cosine 2x. Very important. This is what we will look and call the power rule. Right here, so. Right? But let me finish that and then come to this, because when I do that one, this one will be so much easier for you. All right, let's go now. So let us look at y equals cosine 2x plus 1. Remember, I cannot go inside of the angle to interfere with it. It is illegal. So what I have to do if I'm finding the derivative of cosine 2x plus 1, remember when I differentiate cosine, I get minus sine. So it is going to be minus sine 2x plus 1. However, I must now differentiate the angle. The differential of a constant is always equal to 0. So when I differentiate 1, I'm going to get 0. But the differential of 2x is going to be 2. And see the 2 right here, so I'm going to multiply minus sine 2x plus 1 by 2 to give me negative 2 sine 2x plus 1. Very important. So again, the differential of sine is equal to cosine. The differential of cosine is equal to minus sine. Now, watch this trick. Because when I have sine x, look at what I'm doing. The differential of sine x is cosine x, but I'm also differentiating this x. What is the differential of x? Somebody say 1.
Yeah, 1.
Right. But 1 is known as the multiplicative identity. So there is a 1 in front of this cosine x that I'm multiplying by. Do not see it, but we know that it's there. Watch me. The differential of sine is cosine. So when I differentiate sine x squared, I'm going to get cosine x squared. But it is not finished. I must get inside of the angle now to differentiate. When I differentiate x squared, what do I get?
2x.
I get 2x. So my final answer is going to be 2x cosine x squared. Remember, the differential of sine x is cosine x. The differential of cosine x is negative sine x. When I'm differentiating, and I have an angle greater than x, I differentiate normally, but I'll have to go inside of the angle to differentiate and multiply my differential by the function that I got, the differentiated function. Very important. Fundamentally, the differentiation of sine x is cosine x. The differentiation of cosine x is negative sine x. Right?
Sir said it doesn't matter where you put the x, why you put the x in front of the cosine.
No, because the differentiation of x squared is 2x, not x2, but 2x. Let us look at this one here now. The differential of cosine is negative sine. The differential of cosine is negative sine. So my answer is going to be negative sine 4x squared minus 1. But that is incomplete. The differential of cosine is negative sine. So I'm going to have negative sine 4x squared. I have to provide the angle. And when I move to the exponential function, you're going to see what happens. The exponential function is very cute. She has a very cute sense of humor. So when I differentiate she, I get her back. When I integrate she, I get her back. She's just plentiful. She don't want to go nowhere. She don't want to leave me at all. When I differentiate her, I get her back. When I integrate her, I still have her. When you differentiate cosine 4x squared minus 1, remember you can't get into the angle. So you're going to differentiate everything as a whole and then go and differentiate the inside of the angle. So the differential of cosine 4x squared minus 1 is going to be negative sine 4x squared minus 1. But now I'm required to differentiate 4x squared minus 1. The differential of 4x squared minus 1 is
minus 8.
It's going to be 8x. So all of that answer is going to be So I put in an extra line here. Watch me now. Watch me. The differential of cosine 4x squared minus 1 is going to be negative sine 4x squared minus 1. But I have to multiply that now by the differential of the inside. I have to multiply that by the differential of the inside. See the dot here as my multiplication sign. And when I differentiate it inside the parentheses, I'm going to get 8x. So when I multiply 8x by negative sine 4x squared minus 1, I'm going to get negative 8x sine 4x squared minus 1. Is that clear?
Yes, sir.
Look at number 5 for me, please. I need to stretch my legs. I'm just going to walk around in my space. Ouch. Look at number 5 for me, please, and tell me if you agree with it. And then I'm going to write one for you, and then I'm moving to the power rule. Ouch. Tell me if you get it.
Yes, sir.
Are you seeing that?
Yes, sir.
Yes, sir.
All right, cool. All right. Are there any questions? No questions?
No, sir.
No, sir.
Okay. No problemo, no problemo, no problemo. You know your teacher love to copy and paste. Can you do number 6 for me, please? Finish?
Yes, sir.
Yes, sir.
Yes, sir.
John Mark, you finish?
Not yet, sir. Not yet.
Hurry up because I'm waiting on you to tell me the answer. So hurry up. Johnny, what do you get? Manisha, finish?
Yes, sir.
What do you get for the answer?
2x plus 5 cosine bracket 5x minus 2 minus 7 sine bracket 7x plus 1.
Tell me if what I have on screen is what it is that you got.
Yes, sir.
Yes, sir.
Yes, sir.
Very good. Excellent. Johnny, I still need your answer.
So it look like a wrong question there, sir. Wrong question there.
Okay. Look at number 6 for me, please, Papa.
I'm looking, sir.
Look at it for me, please. I need to move on, but I want to make sure that you understand it. Aniki,
Yes, sir.
you good?
Yes, sir. Let me get.
Nice.
Yes, sir. I understand now.
Very nice, Papa. No child will be left behind. Tati G, all right? Yeah, I hear you now. Yeah, I hear you say nothing more. All right?
Yes, sir. I'm fine.
Nice. Kamisha, type and let me know if you're all right, please, homie. Okay, make sure you know. Oh, all right, very nice. Shante, you good?
Yes, sir.
Cool. Javier, how you stay?
I'm good.
Me know you're good. Matty, you all right, don't?
Yes, sir.
Nice. Natty H, you all right? Where's Natalia Buckley? If I take her lunch money, see, she don't come to school for the rest of the week. I can't believe Natalia don't come to class tonight. What should be on her? Natty H, you all right?
Yes, sir.
All right, very nice. I'm happy. I'm moving on then. I'm moving on. All right, so I'm going to be moving into my power rule. Let me just put everything up here one time. Both. Power rule. Don't blink. I'm going to go through it. I'm going to see what is happening. And you know what Sir did? Sir, the only type of cities that you can understand what is happening. So it says to apply the chain rule in the differentiation of composite functions. Yeah, man. Them something a composite means they have a function of a function. Watch me. Given y is equals to, Tanya, here goes the question now, Tanya. Given y is equal to 2x plus 5 all squared sine dy by dx. So you can go put f of x, f dash of x. Or you can go put y dash of x because them say sine dy by dx. So they are telling you now that they want you to, the form that they want to use is not y dash, but dy by dx. You see the point?
Yes, sir.
All right, good. Let's go. So they're asking us to differentiate this, and I'm going to work with it. This is a power rule. Function of a function. Composite function. Watch me. Ouch. I am differentiating just like how Sir taught me to differentiate. Watch me. That 2 air going to multiply air and drop in front of air, and they reduce air by 1. Just as how we have been doing it. I'm using this 2 to multiply. It goes in front of my product, of my function, and I'm reducing the power by 1. Watch me. This 2 is this 2. I'm writing at my function, and I'm reducing this 2 by 1. It now leaves 1. But what is important, just like with my trigonometric ratios just now, with the differentiation of sine and cosine, I have to now go inside the parentheses and differentiate. The differential of 5, a constant, is equal to 0. But the differentiation of 2x is going to give me 2. So see here, multiply by this 2. So it is times 2 is obtained from the differential of what is inside the parentheses. You will always multiply by the differential of the inside of the parentheses. Every single time. Just as how, Sir, I like teaching with stories, because stories make you connect. You can have connections. You can make connections with what it is that you're doing. So just as how you're doing the trigonometric ratios, cosine 2x plus 1. The differential of cosine is negative sine, so it's going to be negative sine 2x plus 1. But you have to go inside of the parentheses, inside of the angle brackets, and differentiate it, and then multiply it by that to the function. Same thing right here, so. Same thing right here, so. So I want you to note, we are required to differentiate inside the parentheses. To apply the power rule, the index must not be equal to 1. So in order for you to apply the power rule, I can't say 2x plus 5 to the first power. It must be a power that is greater than 1. It must be a power that is greater than 1. Must be a power that is greater than 1. All right, so let's go now. So this 2 out here, so, is going to multiply this 2 here, so, to give me this 4 right here, so. And then 2x plus 5 to the first power is simply 2x plus 5. I don't have to write the first power. That's understood.
That again, please.
This 2 is being multiplied by this 2 on the outside here to give me this 4. And the terms in the parentheses, I'm writing them back, 2x plus 5. See here, 2 times 2 is 4. I'm right back with the parentheses on top. Look at it and tell me if you see that.
Yes, sir. Sir, for the second statement that you wrote, the index that they're talking about is in the question.
Yeah, up here, so the index or power. You know what index is another name for index is power?
Yes, sir. And
Yeah. Or
exponent.
exponent, right. And then finally, it's so long taking a break because I want you to process it. So when I pause, don't pause at me, you know. When I pause, it's deliberate. Watch me now. 4 times 2x is going to be 8x, and 4 times 5 is 20. That's how we apply the power rule. I'm going to prove the power rule for you. But how I'm going to prove the power rule? I'm going to prove the power rule using the chain rule that we just learned. But if they give you a power rule in the exam, please do not do what I'm doing right now because it may make an error. Let me show you what I'm talking about. Same question. Let y be equal to 2x plus 5 raised to the second power, find dy by dx. I know that 2x plus 5 all squares is the same thing as 2x plus 5 times 2x plus 5. In Jesus' name, please do not go into the exam and give a question like this and you decide that to expand it like this. Because you may go into the exam to expand it and do rubbish and get 0 per question, that if you apply the power rule, you could get 5 out of 5. I'm only doing this to prove to you that the power rule works and that the answer that we got for the power rule, if we use another method, we'll get the same answer. In Jesus' name. Amen. All right, let's go. I'm foiling. Two x times 2x is 4x squared. 2x times 5 is 10x. 5 times 2x is 10x. And 5 times 5 is 25. Grouping my like terms together. Grouping my like terms together. Only the middle ones are alike. So I'm going to write out my 4x squared. Add my middle terms. 10x plus 10x is 20x. And my constant 25 is the only term, so I put it back. Notice I don't start differentiation yet, you know. I don't start my differentiation yet. So let us differentiate now. 2 times 4 is 8. Reduce it by 1, 8x. The differential of 20x is going to be 20. And the differential of 25 is equal to?
0.
0.
Why is that so?
So differentiation of a constant. 0.
Constant equals 0.
Very good. Now, if you not ask a question, I don't want nobody to say to themselves, duh, sir. I ask a question for emphasis. Just tell me. Because some of you think that you know it, and you're the ones going to go into the exam and write back the number and give it to me. So the differential of a constant is equal to 0. Yesterday, today, and always. So proving that if I use the power rule up here, so I get by the same something right here. So no, sir, but the power rule does much something, sir. No. Because me I write it and I explain it. That's why it look like that. Good to go, man. Oh, come on. All right. So on there. Example 2. Do now for me, please. Anybody finish?
Yes, sir.
Mm-hmm. All right. What you got for your answer? Talk to me now. What did you get for your answer?
45x minus 50.
Sir, I got 45x minus 15 raised to the fourth power.
Yeah, so you want to know them say 45?
Sir, 45x.
45? Anybody got that?
Yes, sir.
Yes, sir.
Tantan, explain the 40. Ah, did you say 45x minus 15, Tantan?
Yes, sir.
Was that a yes?
Yes, sir.
I'm so happy you made that unforgivable sin, because this now becomes a teachable moment. So she got up to this point, but she went further. Watch me. This is not 3x minus 1, you know. This is 3x minus 1 to the fourth power. Recall? Remember BOMDAS? PEMDAS? In foreign, they call it PEMDAS. And I prefer PEMDAS to BOMDAS, because you see better. PEMDAS is parenthesis, exponent before multiplication and division, followed by addition and subtraction. My parenthesis, my exponent. So I will have to look at my parentheses first, work on my exponent next before I do my multiplication. Now, do you recognize that this is being raised to the fourth power? I cannot do a multiplication before I evaluate or simplify my exponent. BOMDAS, PEMDAS is telling us the same thing. Brackets of multiplication and division before addition and subtraction. Parenthesis exponents, multiplication and division before addition and subtraction. What it is saying for BOMDAS, that we have to work out our brackets first. The O is the order, and the order means the power to which it's raised. And the power to which it's raised is the same thing as exponent. So sometimes you hear me say, open the bracket. Hello, that is ghetto. Open your parentheses, because the correct name is parentheses, but in this part of the globe, we call it brackets. It me can go down a town and say, anybody know where is Matthews Lane? How would they call it?
Repeat, sir.
I cannot go downtown and ask anybody to show me where Matthews Lane is. Tell me the man them call it down a town.
Matthew.
Matthews.
Matthews Lane. So me ever go downtown and I said, excuse me, sir, do you know where Matthews Lane is? They're going to say I want foreigner that make me rob him. And I'm in no way, shape, or form saying it's bad people live downtown, don't get me wrong. But I can tell you, say him don't come from the area because nobody call it Matthews Lane. But that's what it name. The man them call it Matthews Lane. Who says I have conjunctivitis? You have red eye or pink eye?
Yeah.
Running belly, loose bowels, diarrhea. People can't even spell diarrhea to blow out. My belly are run. So I'm just saying to you, brackets is synonymous with parentheses. The order is synonymous with the exponent, and the multiplication, division, addition, and subtraction is the same. So what I'm saying to you here, I cannot multiply this 15 through here before I expand. Watch it. You know what I had to do here? I had to expand here first before I can do any sort of the multiplication here. So very important. Tantan, am I clear?
Yes, sir.
Very good. No, this is the point where you're supposed to make a mistake, And I don't want to be no way about it. Oh, I have made many mistakes. Look what tonight I made mistakes. Come here, type on nothing, that's what I type. Maybe I should sleep to my eye. You understand? But guess what? I'm going to use it again as a teachable moment. You see, if Daniel wasn't one of those talkers in class, should I have it in our book and leave it at misconception? And there are some of you in the class that if I don't call upon Uno, now unmute to talk to teacher and say, yes, sir, I understand. And it is going to be to your demise. I need to know what you are thinking so that I can pause the class and correct the misconception. It's like I pause the class a while ago and remind you of bomb that I'm down. I want the opportunity to get what it is in your headspace. Just like when you go and doctor, and the doctor say, how long ago have you been having this high temperature? And you tell the doctor said, okay. In the doctor's headspace, he or she is ruling out some stuff. So we are doctoring the mathematics. We want to hear what conception or misconceptions you have, because in any given class, Miss can tell you when you write a good lesson plan in any given class, you may have to throw away that lesson plan because you recognize that the prerequisites are not met, or there are many misconceptions and you have to correct those before you move on. It's very important that you speak to me and speak loudly so that I can hear. All right. Because of that error, I want to just make sure to say, oh, sorry. Okay, let me finish that thought. Make sure to understand it. I'm going to give you another one. Look here. You recognize what the first one took me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. You saw how short this one is? That's what I'm telling you. The first one is longer because it is that I am explaining myself as I go along, just to make sure that you're understanding, and I'm making notes as we go along. All right. I'm giving you this one here. On the mark, get set and go. Mm. Anybody finish?
Yes, sir.
Yes, sir.
Good. You guys are worky while I was stretching my leg. Um, Very important, guys. Every now and again, when we are having our night classes like that, just get up and stand up here to help with the circulation, please. Very important. I mean, not tell you to walk go road, you know, but just walk around. Just space around. It's very important for the circulation. And if you're sitting up, keep moving your legs as if you're walking so that you can push the blood back up through your system. Very important. All right, where are we? I am right here. So it's going to be, what's the answer?
Negative 42, bracket 2 minus 7x raised to the fifth power.
That must sound right. Is she right?
Yes, sir. That again.
7 6 is 42. She are correct. Very nice. This is how I like feeling when I'm teaching students and students are learning. Negative 42 times 2x, sorry, 2 minus 7x to the fifth power. All agreed? All aboard?
Yes, yes, sir.
Yes,
Very
sir.
good. Very good. All right. Let me just do it because it's easy. Exponential function. Let me just double check something here. Yes, differentiate exponential and logarithm function. Every now and again, I have to go back. That's 2.6. I have to go back and look at the syllabus. 2.6 differentiate exponential and logarithm function. 2.6. Oh, see there? 2.6 differentiate. Okay, I'm correct. So every now and again, I have to go back just to make sure that I have syllabus coverage. Very important. And that I have syllabus coverage. All right. I want to talk about it right here because I'm going to be doing some other additional questions with you and you will see it. The differential of an exponential function is the exponential function itself. That's the story I wanted to tell a long time. It was the sweetest sauce, and I couldn't wait until I get here. So tell me again. The differential of an exponential function is the exponential function itself. Look at example 1. The differential of an exponential function is the exponential function itself. Look here. Given y equals e to the x, dy by dx is equals to e to the x. The differential of an exponential function is the exponential function itself. Sir, we're going to get that. All right. E to the 1x. Look at my green. Let me bigify it. I use green because I know it's very faint and you can't see it. I really don't want you to see it. So that's why I use that neon green. E to the 1x, e, the exponential function, raised to the 1x. When I find dy by dx, remember I said to you, the exponential function is the exponential function itself. So this e to the 1x, see here, so e to the 1x. But I'm going to differentiate the power now and multiply by everything. So that's why this one comes right here, because I'm differentiating the power 1x. I'm going to differentiate 1x, I'm going to get 1. So that's why the 1 comes here. Let us look at it. The second example. E to the 2x. The differential of e to the 2x is e to the 2x. See here? E to the 2x. But I'm going to multiply by the power. I'm multiplying by the differential of the power. Sorry, I keep saying that. I'm multiplying by the differential of the power. When I differentiate the power, the differential of 2x is going to be a 2. So that's why it's right here. Let's just try e to the 3x. The differential of e to the 3x is 3x, is e to the 3x, multiplied by the differential of the power. I'm going to differentiate 3x, I'm going to get 3, so it's 3e to the 3x. Watch this one. By the way, are you okay with these up here, sir?
Yes, sir.
Yes, sir.
All right, good job hearing you. Y equals e to the x squared. The differential of e to the x squared is e to the x squared. See it here? E to the x squared. But now I need to differentiate x squared. When I differentiate x squared, what do I get? Say 2x.
2x.
See it here? And that's why I get a 2x. So my final answer is going to be 2x e to the x squared. Watch this. Y is equal to e raised to the 3x squared plus 5x minus 7. Find dy by dx. Dy by dx is going to be e raised to the 3x squared plus 5x minus 7. See here? E raised to the 3x squared plus 5x minus 7. The differential of the exponential function is the exponential function itself times the differential of the power. So now I need to differentiate the power. When I differentiate 3x squared plus 5x minus 7, what do I get?
6x plus 5.
And that's why I have my 6x plus 5. You multiply everything right here. I don't want to do this one yet because I don't teach you the quotient rule yet. So soon come on this one. All right? But the differential of the exponential function is the exponential function itself times by the differential of the power or the exponent or the index. So it's pretty easy. There's no too biggie about it. The differential of the exponential function is the exponential function itself. Those I can't go through yet because those are involves the product, and I don't want to do the product rule yet. I have 5 minutes. I just want to sing something for you. I think I'm an excellent singer. Nobody can sing like me. Watch this. First song, product rule. The first times the differential of the second plus the second times the differential of the first. Song done. The first times the differential of the second plus the second times the differential of the first. The first times the differentiation of the second plus the second times the differentiation of the first. Sir, I don't see differentiation there. Differentiation, differential, same thing. The first times the differential of the second plus the second times the differential of the first. This is what the product rule says. The first times the differential of the second plus the second times the differential of the first. Very important that you hear this and hear this several times. So come next class, God's willing, when we are moving into the product and quotient rules, this is not strange to you. Remember what Sir does? He introduces what is his starting point for the next class. Hopefully you'll think about it. The first times the differential of the second plus the second times the differential of the first. That's what the product rule says. The quotient rule says the denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Sir, I did add maths, and I did unit 1 maths, and I did some levels of differentiation, and at the first term, you say something like this, and I would agree with you. I would agree with you. Because what it is that your teacher would have given is u dv by dx plus b du by dx. True or false?
True.
Yeah. It's the same thing though. It works out to be the same thing. I learned that method. I learned that method too. But guess what? I came across this method and it is a sweet, it's nice, like a nice pot of oxtail with broad bean and some gungo, green gungo, not dry gungo, green gungo. And I tell you, the gravy nice on something. Oxtail bone soft. My God. Thank you, Jesus. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Then, sir, what if I understand u dv by dx plus v du by dx? Sir, may I have to use your method? No. You don't have to use it. Whichever one you find most comfortable, that you want to use. Because I know your method too. I know your method too. But whichever makes it easier for you, I chose one of the two methods because this one sounded nice. When I exam and I did the question, I just start singing my song. The first times the differentiation of the second plus the second times the differentiation of the first. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Very important. I'm going to end here and I'm going to ask you, what was the take-home point for you for class tonight? Anybody, somebody?
Differentiation of a constant is 0.
Very good. The differentiation of a constant is equal to 0. Yesterday, today, and tomorrow. Somebody else. What was the take-home lesson for you tonight?
The question.
Go ahead.
With the when I did do the exam for the two, let me go say like the question we can trouble at two.
The power rule?
Yes, that.
Okay, power rule. Okay, very good. Remember, you differentiate as you would differentiate normally, but for the power rule, you have to differentiate inside the parentheses and then multiply by the differentiation. One other person, what was the take home for you for tonight?
The entire
the entire what, John Mark? Where's it?
entire lesson, sir.
You're too kind. Very good. Nikki, were you coming in a while ago? Nikki?
Yes, I was going to say about the first principle, sir.
I didn't, because what happened is that when I look back at your syllabus, I recognize you're saying that I don't have to. So that is some knowledge that you get that you can move on with. If you're doing pure maths, it is going to come in very useful. But if you're not doing pure maths, don't worry about it. You know, no knowledge is wasted knowledge. And I'm going to say one thing quickly. I heard Mrs. Henningham, when I had my mishap the other night, some Fridays ago, I heard her, speaking to her about a matter. And she was saying that she can find many examples to talk to you about. And trust me, when you have experience, you can share those experiences. There are times, some of you say, and again, Mrs. Henneman asked in class last week, what do you want to become? And quite a number of you said, I want to become a veterinarian, or I want to move into forensics. And I said to the person or persons, what is your backup plan? It is extremely critical that you have a backup plan, because sometimes it becomes very difficult to get into your first option, and you can't sit down and be a perpetual student waiting to get in, money out there to make. So if forensic science is your first option, you need to know at this stage why if forensic science will work out, the bio grade not too bad, I'm going to move into dentistry, or I'm going to move into pharmacy, or I'm going to move into medical technology, or I'm going to move over into nursing. But make sure that you have a backup plan. Trust me, teaching was the furthest thing to my mind. A long time I teach, from me there, you and me I teach my friend them. We go to class and sit down just to learn, but go back and teach. Because I just love the idea, but teaching was not what I wanted to do. Far from what I wanted to do. So sometimes we can't turn our backs on a profession to say, oh, I will never do that. I know exactly what I want. Me this says so too. You couldn't tell me, say, I was going to be that all my life. I'm singing on that. What you want to become? Oh, yeah, bam, 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 bam. Oh, you know what you want to become? Long time from a born. And look at what I'm doing. Sitting down and teaching. So I'm saying to you, you don't know what may come up. You may end up deciding that, no there, never teach. Bam, you have to teach a math class. Bam, first principles come up. But we never did first principles in Cape integrated math. Oh, but we did go to class with Mr. Shanpa one Saturday now. And we didn't catch it. No information is wasted. Once it is that you gain knowledge, it can never go to waste. Never. So I'm saying this to say to you guys, please study. May 2 is fast approaching. I got the information, I got some of the data today from the CXC past something for the English and math. I sent it off to Mr. Russell so we can start the analysis of the stuff so we can have further conversation. So that's why I never come to the class with it, because it's only this morning I'm getting some other stuff. Don't even get all of them yet, but I'm hoping before the week is out, I will get the additional stuff so we can tabulate the results and we can share them in the class. But please, guys, remember, importantly, have a relationship with the Maker. Say gentle Jesus before you go to bed. See if you can get up and do some work before the day starts tomorrow. Your work day starts tomorrow. Have a good one, and thanks for coming out and participating and learning. All right? Later.
Yes,
Bye,
sir.
sir.
Thank you, sir. Bye, sir.
Yeah, man. I do you as a father. Do